Okay, here we go with part 2. This one's an algebraic vector example from 7.4. How I'm going to get going here is by, I'm actually going to draw a diagram. And it's not going to be to scale or anything like that, but I'm going to have my two vectors, x and y. There's x and there's y, and it's defined, this parallelogram is defined by these two vectors. So I can write them tip to tail, draw them tip to tail, and show the parallelogram, and there it is, dandy. Find the angle between the diagonals. Okay, well, let's do that. There's one of the diagonals, and there's another diagonal. And I put, by the way, I put arrows on those on purpose. Well, how would I get an expression for the diagonals? The diagonals, this one here is just x plus y, right? That's what this one is. What's this one then? Well, this is going to be, start at the start, negative y is this way. That's negative y plus x. This is x minus y. And how do I get the angle between the diagonals? Well, the formula I know is any vector dot any other vector is the magnitude of A times the magnitude of B times cos of the angle that's between them. That's what I want, right? That's what I'm looking for. So I can handle this by using the dot product. So let's use the dot product. I'm going to have the magnitude of x plus y times the magnitude of x minus y. Oh, sorry, excuse me. Oh, hang on, I can do this. What it is, the dot product of those two. I'm going to have the dot product of those two vectors is equal to the magnitude times the cos of the angle between them, and that's what I want to find. So it means these other all these other things I must be able to calculate, and I'm going to kind of in my rough work here on the in the margin, I'm going to calculate those. So first of all, x plus y is just a little bit of algebraic vector action. 0, 8, and 4. X minus y is is 2, negative 4, 4, I believe. Let me just check that, make sure my arithmetic's okay. 2, negative 4, 4, and 0, 8, 4. All that looks good. So that's this side is 0, 8, 4 dot 2, negative 4, 4. And then the magnitude of that, well, the magnitude of this vector, let me do that over here. The magnitude of 0, 8, 4 is just square root of 0 squared, 8 squared plus 4 squared, 64 plus 16, square root of 80. Magnitude of this one is the square root of 2 squared plus 4 squared is 16 and 16 is 32 plus 4 is 36, which is 6. There's old 6. And so this is square root of 80. This is 6. And this is what I want. And so all I'd have to do is divide this dot product. And remember how I do the dot product of algebraic vectors is I multiply and add as I go. 0 times 2 is 0. Plus 8 times negative 4 is negative 32. Plus 4 times 4 is 16. And then I divide it by square root of 80 times 6 on the bottom there, and I get cos of theta is equal to negative 16 over 6 root 80. And so I'll do the inverse cos of that. Oops. Theta equals the inverse cos of negative 16 over 6 root 80, which is, clunk, 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 in degrees around 107 degrees, which is strange in our diagram that we have a obtuse angle, but not that strange, right? Because it kind of looks like there's two angles. And remember, the angle between two vectors is when they're drawn tip to tail, or tail to tail rather. Does that angle look like it's 107 degrees? Well, it doesn't really matter because my diagram wasn't to scale. So my conclusion here is, therefore, the diagonals meet at 107 degrees. If I would have said, if you could have said 73 rather, the acute angle, I probably wouldn't argue too hard about that. But that's it. That's that example.